So it is, sometime after 6 o'clock. I know it is late. I wanted to try to do a fun, light talk. And so I thought I would do something involving one of my favorite Sesame Street characters. How many of you have seen Cookie Monster at some point in your life? All right. I need you to be familiar with the original classic Cookie Monster, who always eats cookies. The current politically correct Cookie Monster would actually not be sufficient for proving the theorems I need. Okay. So, a couple of things. You can ask. The goals of this talk is you can join in. You do not need to know too much mathematics to get involved in this. There's at least one person in the audience right now who started working with me when he knew some, but not nearly as much mathematics as he knows now. One of the things you learn is the need to ask the right questions. So a lot of times natural problems are missed. One of my colleagues was giving a talk a couple of years ago on problems related to this. And because I had different training than he did, as he's giving his talk and he's explaining how continued fractions solve all of this stuff, but give you all these other difficulties and technical obstructions, and going, well, if you throw all of that away, you look at it from a different point of view, it becomes a combinatorics problem. And not only can I prove what you want, I can prove a lot more. So I really want to emphasize what questions to ask, the right perspectives to ask. So we'll be seeing generating functions and partial fractions. How many of you remember partial fractions from Calc 2? There is a reason behind sadistic professors, well, sorry, not behind, other than sadistic professors as to why you learn partial fractions. Partial fractions is actually an extremely important technique for analyzing a lot of problems, and I want to try to make you like partial fractions a little bit more. And then as time permits, I will end with open questions. There are a lot of patterns to be investigated. There are patterns hidden everywhere, including the slides. Okay. The slide advance does not seem to want to work anymore. Well, it worked for a minute. All right. Let's try again.
Infected with Windows?
We had this problem a moment ago, and I actually had Lee take away his computer.
Did he take his laptop?
I think he did take his laptop.
Yeah, I'll run it.
And so,
Oh, it is Windows.
Alright, everybody take out your smartphones and go to the following URL.
Yeah,
So we actually tested it before.
Blackboard.
Alright, how many of you have seen the Fibonacci numbers? Okay. How do you define the Fibonacci numbers? Well,
with a
recurrence?
Recurrence or with
I'm sorry?
in closed form or with recurrence?
No, recurrence is fine.
Like 1, and then you just next
Okay.
fn is equal to fn minus 1 plus fn minus 1.
Okay. So we will put that in reserve. So hopefully this will now toggle back. Okay, I really just like seeing professors run around. Okay. So, quick review of probability. I don't need to know too much about probability, but to analyze the Fibonacci numbers and some of their nice properties, I need 4 concepts. The first is, what does it mean to be a random variable with a probability density? It means I have some non-negative function that integrates to 1, and the probability my variable takes on a value between a and b is just the area under the curve from a to b. So if you've ever taken a calculus class and done the fundamental theorem of calculus without hearing the word probability, I apologize. This is why we care about integration. Integration gives us areas under curves. It's not because we like calculating areas under curves, it's because these areas under curves have meaning. It's the probability of an event happening. If you have ever taken a class, you know what the mean and the variance is. You have the average value and how spread out you are. At Harvard, I would actually give higher moments such as the kurtosis and skewness. I was visiting a friend at Harvard years ago, and in one of the med school classes, they listed the first 4 moments of the distribution, so you could really compare yourselves to your classmates. For us, the mean and the variance is more than enough here at Yale. You know, average value, and I'd just like to see you move. The last is the Gaussian. If you've ever taken a large class, you don't have to grade on a curve. The curve is almost forced upon you by the laws of mathematics. It's a wonderful distribution. It's also called the bell curve. It's called the Gaussian. Anything with this many names must be important. Its density function is some normalizing constant, e to the minus x minus mu squared divided by 2 sigma squared. All right, so that's essentially all the probability I need. I need just a little bit of combinatorics. n factorial is the number of ways to order n people when order matters. N choose k, lots of different ways to write it. It's the number of ways to choose k people from n when order doesn't matter. So think of it as choosing representatives, not choosing opposite. There should be a difference between president and secretary. And the last is Stirling's formula. If n is large, n factorial is approximately n to the n e to the minus n squared of 2 pi n. If you've taken enough calculus to have seen the integral test, you can use the integral test to get a pretty good approximation of Stirling's formula without too much work. Okay, Fibonacci numbers. So as has been suggested, we have this recurrence relation. I choose to start at fn plus 1. You can choose lots of different ways. And then you gave me, who was it who spoke up? Are you my morsel or was my morsel?
I am morsel.
Excellent. So you start off with 1, 1.
Or 0, 1.
Or 0, 1. There is another. I feel like Yoda talking to Obi-Wan Kenobi, which I hope your generation remembers. There is another way to start the Fibonacci numbers.
0, 0, 1.
No.
Negative 1.
No. See,
You mean
wonder
start
how
the
you can feel
recurrence or
it.
define the numbers?
No, I want essentially the same sequence, but I want to start it differently. I don't like 0, 1. I don't like 1, 1. I don't like starting with negatives. What do I want?
1, 2.
1, 2. 1, 2 is the right way to go. And the reason I want 1, 2 is because of the following. We have Zeckendorf's theorem. Every positive integer can be written uniquely as a sum of non-consecutive Fibonacci numbers. Well, now hopefully it is clear why I don't want to have 0, 1, 1. I lose uniqueness. It turns out that this is equivalent to the definition of the Fibonacci numbers. The Fibonacci numbers are the unique sequence such that every positive integer can be written uniquely as a non-adjacent sum. And instead of doing non-adjacent sum, you can look at other types of decompositions. So what I want to do today, greetings, grab some pizza crumbs and apples. So I want to talk about generalizations of these Zeckendorf type decompositions. So you can probably tell when I first started speaking about the subject, here is a completely random number, 2012. I can decompose it in the following manner. Where am I from?
Where are you from?
Yes.
Originally?
Yes.
Is it New Jersey? Wow.
Try again.
Where is it?
Boston.
Yeah.
Boston.
I remember it very clearly.
So as a Bostonian, I will not pronounce this theorem. I will digitally add it to the recording later. But this person was able to prove the following result, which is a very natural question to ask if you have a Zeckendorf decomposition. On average, how many terms do I need in my decomposition? Well, some numbers are only going to require 1 term. Other numbers, if it's every other one, are going to require many. So I need some way to figure out what's the correct scale to study a problem like this. And the correct scale to look at is, you know what, let's look at all numbers from fn to fn plus 1. These numbers are all going to be approximately the same size. They're going to all have the same candidate set. If I'm greater than fn and less than fn plus 1, fn has to be one of my summands. And then the other one's up for grabs. So this is a really good region to investigate. And what Lucky proved is that the number of summands I need on average is about n over phi squared plus 1, where phi is the golden mean, or almost a quarter n. If you think about it, the most you could have is n halves, the least you could have is 0. The arithmetic mean of the two of them would be n quarters, pretty close to that. You know, rough ballpark estimate, we're in an engineering building, not bad to say something along those lines. Once you ask this, though, you can start asking more refined questions. You can ask about the fluctuations about the mean. And so you get a central limit type theorem. So this was actually known for the Fibonacci's before we started looking at it, but we were able to prove it exists in other situations as well. And so, as n goes to infinity, if you look at the numbers between fn and fn plus 1, for each one of them you count how many summands they have, you plot how many you have, you get something that's normally distributed. After you see that, you can ask more questions. You can ask, well, what about the waiting times? So most of my life I spend studying waiting between events. Okay? You know, how long till the pizza gets, different things, how long do I have to wait? This summer I'm going to be looking at spacings between primes, so spacings between zeros of the Riemann zeta function. How long do I wait before I get the next thing? Here I'm waiting between summands. And there's two ways to do it, depending on how much nuts and bolts you want to get into. One thing I can do is for each number m, I look at its decomposition, and I look at how many gaps of length 2 do I have, how many of length 3, how many of length 4, how many of length 5. And I put all those gaps in a giant bin. and I see what fraction of all the gaps are 2, what fraction of all the gaps are 3, what fraction of all the gaps, I can figure it out. The other thing I can do is for each one of them, I can create a histogram and see how many of that number's gaps are 2, how many of that number's gaps are 3. So do I do it for all of them by averaging, or do I do it one at a time? Not surprisingly, doing it one at a time is a bit harder. Turns out you get the same answer in both cases. In this case, it's for almost all m, you will see the same behavior as the average. If you've ever taken a class in probability, it's kind of like a central limit theorem kicking in. And so what we get is that the gap measures converge almost surely to the average gap measure, which is a geometric decay. So the probability of having 5 gaps versus having 6 gaps, there's a decrease in probability by 1 over phi, where phi is the golden mean. And so I just tried to find 2 different ways of plotting it to try to show information. This is the probabilities of different gap sizes, and then this is the ratio of n to n plus 1 for my gaps, or k to k plus 1. And if you look at it, you see it's very close to the geometric mean. So I guess if it's to the golden mean. So if I'm doing it this way, I must be looking at gaps of size k divided by gaps of size k plus 1 to make it larger. One thing that I find interesting is, this little y coming in at the end over here. This might be a good school to try to investigate the structure of that. Is there any deeper reasoning for why we're going off like that? Alright, the last one that I want to just briefly mention is the longest gap. So how long do I have to wait, for a typical m? And the answer is a beautiful double exponential. You almost never see a double exponential unless you are doing a cookbook problem in a calculus class where they just want to make sure you know your rules of differentiation. This is one of the few situations where the double exponential arises very naturally. It's very similar to what you would get if you take a fair coin, or more generally a biased coin with probability p of heads, and keep flipping it and ask, what's the longest run of heads as I keep flipping this coin? And the amazing fact is if you flip the coin n times, the average number of heads is very close to a nice multiple of log n, and the fluctuations are actually bounded independent of n. It's extremely tight convergence. If you look at what's going on over here, I will try to do the algebra live without making a mistake. I want to know the probability my longest gap is at most Fn is the following expression. Let's imagine Fn is log of phi times the log of n. Well, if that's the case, then this is going to be a 0 up here. So let's imagine that Fn equals the log of phi times the log of n plus log, drawing mathematician, n. Just a little bit larger than the mean that I'm predicting. Okay? What happens? Well, if I do the subtraction, I now have e raised to the log n. That's going to be log n. Then I have e to the negative log n. That's 1 over log n, which goes to 0. Not fast, but it goes to 0. So being just a hair smidgen larger than the mean, did I do it the wrong way? Okay. I might have gone on my sense of, rather than going to 0, maybe it's supposed to go to 1. I may have made an algebra mistake. I apologize if I've done so. But the point is that in these calculations, there might be a fact that's making me think that there's a typo on the slide that it goes in the wrong order. But it's incredibly tightly concentrated about the true answer. Okay, so what I want to do now is I want to explain the new way of looking at the problem. And for those of you who were here earlier, I actually explained why I have a Cookie Monster here. This Cookie Monster is because a receipt of mine for $2.70 was denied due to lack of proper itemization. So for those of you in accounting and auditing, here's Cookie Monster. He's at the talk. How many of you have ever heard of the cookie problem or the stars and bars problem? You have C identical cookies, you have P distinct people. And you want to know how many ways can you divide the identical cookies among the distinct people. And so the answer turns out to be C plus P minus 1, choose P minus 1. So again, it doesn't matter which cookies you get, but we will assume that the people are distinct. So think math graduate students, not engineering graduate students. Where in some of these engineering labs, it's not really clear if the professor knows the difference between some of their grad students. In mathematics, we do know who our grad students are and what they're working on. Right? So let me show you how to do this. So consider C plus P minus 1 cookies on a line. The original classic Cookie Monster, he comes and he eats P minus 1 cookies. How many ways can he eat P minus 1 cookies from C plus P minus 1? That's one of the 3 combinatorial facts I told you I needed. It's C plus P minus 1, choose P minus 1. What that has done is that's put in P minus 1 dividers. And the dividers have then partitioned the number of cookies remaining into P sets. So a little bit more explicitly, imagine we have 8 cookies. If you have trouble with theoretical mathematics, we have actual stuff, or we used to have actual stuff there. For those of you who are Jewish like myself, we also have, not quite as tasty, but kosher for Passover cookies. And so you can do the experiment, you can do the divisions afterwards if you want. Imagine we have 8 cookies, we add 5 more, so we have 13. Cookie Monster shows up. This is the original Cookie Monster. He is happy to eat cookies. He eats the following 4 cookies. This is how many cookies go to the first person. Second person, it's not their day, they get none. Third person gets 2. Next person gets 3. Last person gets 1. There is a one-to-one correspondence between the number of ways to eat 4 of 13 cookies as there is to divide 8 cookies among 5 people. And so since we can count one of them very easily, we actually get the other one. Okay. Because this is a math club talk, I really should not be treating you like little kids, like Sesame Street people, so I will put this in a more math language. If you've heard of Waring's problem, or if you've heard of Diophantine equations, what we're doing is we're doing a very simple version. I'm trying to write my integer c as a sum x1 plus dot 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 plus xp, where all the x's are non-negative integers. So this is Waring's problem where the exponents are all 1. I could try to write my number c as a sum of squares, sum of cubes, so on, so on, and so on. Okay, and so we've just solved this problem. There's other ways to solve it, but this is a nice way to solve it. Okay, so how does this help us for the cookie problem? So let's let P and K be the number of numbers in my interval such that the Zeckendorf decomposition has exactly K summands. And so this is the whole heart of the proof. This is probably, I think, holds the record for the longest proof of Zeckendorf's theorem that every number has a unique decomposition in terms of Fibonacci numbers that are not adjacent. So I feel before going into this, let me show you the shorter proof so that you will definitely be hesitant to follow this. So here is the simple proof of Zeckendorf. Greedy algorithm. If you go high enough in mathematics, that's actually enough to get full credit. At the undergraduate stage, you're probably expected to put in a few more details. I know the way my problem sets were graded, that was definitely the case 15, 20 years ago. How many of you have heard of greedy algorithms? Alright, so what it basically does is you give me your number m, take the largest Fibonacci number you can, less than your number, and subtract it. So I take m, and I subtract off the largest Fibonacci number I can. Let's call it fj. I look at what remains, and I subtract the largest Fibonacci number I can. I think k is the next letter in the alphabet. If k was adjacent to j, so if this was really, m minus fj minus fj minus 1, I'm really subtracting their sum. Well, the sum of 2 consecutive Fibonacci's is a Fibonacci. It's a larger Fibonacci number. That violates the fact that this was the largest Fibonacci I could subtract. Therefore, k is not equal to j. And it's not equal to j minus 1. And then this proves, by induction that you have a decomposition. You then just have to show that you have a unique decomposition. That if you had 2 different decompositions of a number that were non-adjacent, that they couldn't somehow work. Not too bad to show that. Okay, so now that you've seen the short greedy algorithm, let me show you the long involved way, which will pay great dividends later. And the idea is we're going to partition our set of numbers between the nth and n plus first Fibonacci number based on the number of summands they have. And that's going to be great for what comes later. So P and K is the number of integers that have exactly K summands in their Zeckendorf decomposition. So what's going on? Well, if I'm in this interval, I have to have Fn. If I don't, the largest I could be is Fn minus 1. I can't have Fn minus 2. So if I add everything up, I won't be able to get into this interval. So I have to have Fn. I don't have the one immediately before it, and then I have to have k minus 1 other indices. And so if I look at my indices, my last index is n, my first index is at least 1, And if I look at all the other indices, the difference between I2 and I1 has to be at least 2, or they'd be adjacent. Similarly, this difference has to be at least 2. This difference only has to be at least 1. You should never try to follow all the algebra live. It's not worth it. Just try to get the big picture and hope I haven't made too much of an algebraic mistake. Let's let D1 be I1 minus 1, DJ, IJ minus 1 minus 2. What I'm doing is I'm throwing away the stuff I know. I know this gap has to be at least 1. I know this gap has to be at least 2. If I sum all the D's, and I sum all the stuff that I had to subtract off that was forced upon me, it's got to add up to n. And so then just bringing the stuff over on the other side or dealing with the subtractions, I get the sum of the D's is n minus 2k plus 1. And I know how to solve that. This is a cookie problem. This is the number of cookies I have k people. So the number of ways to do this is just, after I do some algebra, n minus k choose k minus 1. The way you should look about this is, when we had the decomposition, remember the second person had no cookies? A lot of people would feel that this is not fair, that everybody should get at least 1 cookie before somebody moves on to 2 or 3 cookies. And so you could put constraints. I will only allow myself to consider decompositions of cookies where everybody gets at least 1 cookie. That's not that hard to do. All you do is you say, well, I want each of these x's to be at least 1. Let me write, I just don't like the people on this side of the room as much. Let me write xi as yi plus 1. That means I'm letting yi be the excess in cookies above the number that's forced upon me. And now I would just get y1 plus yk equals c minus k. And so if you want to put in some lower bound constraints on fairness, it's actually very easy to do. Fortunately for the gluttons among us, there is no easy way to put on upper bounds. There's no easy way to force people to have a maximum number of cookies other than a very painful inclusion-exclusion. So, Gaussian behavior. I want to give you a quick proof that the distribution of the number of summands becomes normally distributed. So the proof is the following. Use Stirling's formula. N factorial is about n to the n e to the minus n squared of 2 pi n to approximate the binomial coefficients. And then after a few pages of algebra, you find the probabilities of approximating Gaussian. So you start off like this, and you continue. Where's Owen? So you're working with me this summer, right? You continue a little bit more, a little bit more, a little bit more.
Send me screenshots, Owen.
I'm sorry? You've already signed the papers, right? Continue a little bit more. And then, yeah, good, look, there's a QED symbol, so we stop. Okay, and so this is a proof. This, fits all the qualifications. It solves the problem. It's also not particularly enlightening. You don't really see why it's true. And so I want to go through another way of doing this proof. The other thing is, this method does not generalize well. It crucially involves the fact that I know exactly how many numbers have exactly k summands in the decomposition. And so what I want to talk about is, when you don't have as tractable an expression, what would you do? To me, the most amazing part about all this algebra is that my students did not burn me an effigy or more, is they kept patiently going through all the calculations. Alright, so I want to talk a little bit about generalizations. So instead of looking at the Fibonacci's, let's look at a more general recurrence relation. So I'm going to have a fixed depth of length L, and I'm going to say hn plus 1 is some linear combination. Right now we can only solve it when the c's are non-negative. For some things it's actually easier if the c's are strictly positive. You've seen stuff like this all the time. One of the simplest ones to look at is when you only have one term. If you have one term, you could either be base 2, base b, base 10, maybe hn plus 1 is 10 times hn. And I'm talking about how many terms do I have in a binary decomposition or a decimal decomposition. There is a notion of a legal decomposition. I'm not going to go into it. It's essentially what you would expect. I'm not allowed to use my relation to reduce somehow. An analog of Zeckendorf holds. I'll try to say it once. An analog of Lekkerkerker holds. And then there's also central limit type theorems, similar results about statements and gaps. So what I want to do is I want to show you a little bit about how things change. So the generalized Lekkerkerker's theorem, the coefficients become a little bit more involved. We can write them down explicitly. Yinghui Wang was my student who did all this. She's a graduate student at Columbia now. It was a truly impressive piece of analysis to keep everything so explicit. But you can compute what things are. So we said for the Fibonacci's, the mean number was n over phi squared plus 1. There is some computable constants, c and d, and here is what c is equal to in terms of the recurrence relation we start with. All right, this is probably my favorite slide in terms of just visualness. I like how Cookie Monster is looking at us. You have a central limit type theorem exactly as before. The question is, how do you want to count things? Anybody here read Hardy and Wright? Finally, something where people's hands are not going up. So one of the best pieces of advice is read the masters. Hardy and Wright have a wonderful book on number theory. I strongly urge you to look at this at some point. They talk about how many prime divisors does a typical number have, and what is the distribution of that like. And there's two ways to look at it. I can count just the number of distinct divisors, or I can count the total number of divisors. For something like this, I could count just which indices occur in my decomposition, or I could do a weighted number where, well, if it occurs 5 times, I should count it 5 times. It's a little bit easier to look at the weighted one, and in that you also get Gaussian behavior. Alright, so let me give you an explanation now as to why it's actually not surprising to see Gaussian. So let's take the very special case when hn plus 1 is 10hn. This is the decimal decomposition that you should all know. So legal decomposition, well, we all know how to write numbers in decimal. So if I was really good, I would work that into the talk. But, was it welcome to the Ides of Ma? What? So all of the A's are either 1 through 9, and if you're not the first number, you could also be 0. We're not allowing a number to start with 0 because then it's not in the interval hn plus 1. Well, if you think about how many different ways I can represent numbers, how many numbers do I have? Well, I have a bunch of independent, identically distributed random variables, except for the first one, which is not the same distribution, it's not allowed to be 0. The total number of summands is just the sum of how many do I have in the ones place, how many do I have in the tens place, how many do I have in the hundreds place, and so on and so on and so on. If you know the central limit theorem from probability, sums of independent, identically distributed random variables become normally distributed. And the fact that the first one is 1 to 9, not 0 to 9, is insignificant in the limit, and this is where the central limit theorem comes from. So you can now see a central limit theorem in the special case of decimal. It turns out it just holds in greater generality. So what else can we generalize? Another thing you can do is you can allow plus or minus Fibonacci numbers. And so we call these 5 difference representations. A lot of these results were done by undergraduates at RUs. This was done by Hannah Alpert at, I believe, Minnesota Duluth. And she showed that every integer can be written uniquely as a sum of plus or minus Fibonacci's, such that every 2 terms of the same sign, different index by at least 4, and opposite sign, different index by at least 3. You get a generalized Lekkerkerker theorem as before. Are you surprised that there's about 1 more positive summand than negative summand? Well, I'm decomposing positive numbers, and my first summand has to be a positive number. That's that little bit of a bias. The result is reasonable. You also get a central limit theorem, and you actually get a correlation coefficient in the number of summands that depends on the golden mean, which is nice. All right. So what I want to do is I want to give you an idea of how you would prove this using generating functions. Out of curiosity, how many of you have seen generating functions? Excellent. So have you seen proof of Benet's formula through generating functions? All right, so this is my favorite formula. One of my favorite formulas in all of mathematics, definitely my favorite formula about the Fibonacci numbers. It allows you to jump to any Fibonacci number. The simplest way to prove Benet's formula is the method of divine inspiration. Write it down, and notice it works. Done. Okay? It's the method of divine inspiration. For those of you who are planning on using this on finals in a month or so, it's not always countable. You can't always, count on being divinely inspired in time. And so you definitely want a better method of solving it than just happening to write down the answer. But it's a proof. You can check and see when n equals 1 and 2, it matches what it's supposed to. Here I'm actually going back, I think, to the standard definition of Fibonacci numbers. So here's the proof using generating functions. So I start off with my recurrence relation, and I form a new function. I form the generating function g of x is the sum of all positive integers n of fn x to the n. If you wanted to, you could start the sum at n equals 0. Why don't I start it at n equals 0?
F0, 0.
F0, 0. I've gone back to the original definition of the Fibonacci numbers. There's no need to include F0. If you've never seen generating functions before, this should seem very silly. I'm starting off with a sequence I don't know, and I'm building up a function. And somehow I'm going to deduce information about that function, and then use that to get information about the numbers that build it up, which I don't know. So the amazing fact is that we can actually write down this function in closed form. The reason is, we actually know all the Fibonacci numbers, we just don't know that we know them. Once I give you the first two Fibonacci numbers, everything else is determined. It's all a game of, can I extract that information in a useful way? And so, how many of you have taken differential equations? When you get to series solutions in differential equations, it's also known as, how do I change the index of summation and recognize what I get? You just keep doing this again and again and again with your sequences. And so I have a sum of n greater than or equal to 2. I'm going to write it this way, fn plus 1, x to the n plus 1. And then I'm going to use the Fibonacci relation. And then what you should notice is, these look a lot like the original generating function g. The difference is where the summation starts, and the difference is I have an x to the n plus 1 rather than an x. Not a big deal. You can always play games, pull x's outside, add terms, subtract terms, and as you do this, if you do enough of the algebra, you end up getting g of x minus f1x minus f2x squared is x g of x minus f1 of x plus x squared g of x. You might remember the bring it over method, I'm not sure what they called it when you took calculus, where you get the integral you want to evaluate on both sides of the equation. As long as the coefficient in front of it is not 1, you bring it over to the other side, you get 3/4 the integral I want to evaluate is equal to blah, therefore my integral is 4/3 blah. And so I've got g of x on both sides, I can isolate for g of x. And I get g of x is x over 1 minus x minus x squared. Now if you've seen the Fibonacci's before, this is very similar to the characteristic polynomial of the Fibonacci's. I'm just looking at the reciprocal of the roots rather than the roots. Alright, so we have a generating function that equals this. Now you can see why I mentioned partial fractions. I want to find the numbers fn. Well, I could expand this out. If I try to expand this out directly, it's going to be a mess. I'd have to use the geometric series formula. I have 1 over 1 minus x plus x squared. And when I start expanding this, I get 1 plus x squared plus x squared squared plus dot dot dot. And you can see, I can get an x to the 4th term from the 4th one down, from the square of this, from the, there's lots of different ways, and it becomes a combinatorial nightmare. The way around that is the partial fraction expansion. And so what we do is we write this as, something over 1 minus one of the roots in x over 1 minus the other root in it times x. And so again, after some algebra, you see you have an expression like this. Now we expand each one of these using the geometric series formula. And when we do that, we end up getting, the coefficient of x to the n is just going to be the nth Fibonacci number. And here is Binet's formula. Now what's amazing is every Fibonacci number is an integer, right? If you saw a bunch of numbers in a police lineup and you had to identify the integer, this would not be one of your leading candidates. No. You've got square roots, you've got division by 2. This is an integer. As a fun exercise, what numbers can you replace 5 and 2 with and still get an integer for all choices? So try to figure out when you can replace that and still always get an integer. Alright, the next is differentiating identities. Out of curiosity, how many people have seen differentiating identities? Okay. Identities are the bread and butter of mathematicians. So if you can have an identity, wouldn't it be great if you could generate infinitely many more identities from it for free? Yeah, I feel like I'm selling Ginsu knives. So that's what differentiating identities do. It allows you to start off with something you know, and you can generate more things. So, for those watching at home, they won't see this on the blackboard, but if I look at the sum of x to the n, this is 1 over 1 minus x. Alright, n goes from 0 to infinity. As I have a math degree, I feel compelled to say absolute value of x is less than 1. If I differentiate both sides of this, I have to justify interchanging the derivative of a sum as the sum of a derivative. Is this technically an engineering building?
It's the math department.
It's the math department, but is it technically an engineering building?
We're safe by absolute convergence.
Well, we're definitely safe, but I'm saying if I'm in an engineering building, I don't feel at all a need to justify this. You can justify. The best way to justify this is to note that if you truncate the geometric series, you get a geometric series, and you can write down an explicit formula for the tail, and you can convert to a finite sum. But if you just interchange the sum and the derivative, take x by d by dx on both sides. And the reason I want to do x d by dx is the d by dx will lower the index by 1. If I multiply by x, I raise it back, and I'll get the sum, n goes from 0 to infinity, of n, x to the n, is x over 1 minus x squared. So in particular, if you take x equals 1/2, you get the sum of n over 2 to the n, and it goes from 0 to infinity, if I remember correctly, is just 2. And then of course you could apply this differential operator again and again and again, and generate even more identities. So it's a wonderful, wonderful way to increase your toolbox. And so what we're going to do here is if we have a random variable, and we know the probability x equals 1 is 1/2, probability x equals 2 is 1/4, x equals 3 is 1/8, this is a geometric random variable, we can, use this to figure out things such as the mean, the variance. These are all related to being able to calculate certain sums from probability. And this technique called differentiating identities allows you to do it. The idea is what's called the method of moments. So the mean and the variance are related to the first and the second moments of a probability distribution. It's essentially integrating x to the k p of x dx. And this is the kth moment. And the hope is that if you know all the moments of the distribution, that uniquely determines the distribution. It turns out that is not always the case. There are some distributions that have the same sequence of moments, but they're different. This is very similar to why real analysis is so much harder than complex analysis. If you take complex analysis, once a function is differentiable once, it's differentiable infinitely many times, it equals its own Taylor series expansion. That's wonderful. There are functions in real analysis whose Taylor series converges only at the point you're expanding about, which is not really impressive because the way you write your Taylor series is f of 0 plus f prime of 0 times x plus f double prime of 0 x squared over 2 factorial. Well, everything at the origin, x is going to be 0, so the only term that survives is f of 0, so of course they have to be equal. So the fact that the only point that they equal is the origin is really not that nice. So, how many of you have seen this function? e to the negative 1 over x squared if x does not equal 0, and 0 if x equals 0. So using L'Hopital's rule as an exercise, calculate the derivative of this function at the origin. All the derivatives of this function at the origin equals 0. First derivative, second derivative, third derivative, fourth derivative. So if you write the Taylor series expansion for this function at the origin, it's identically 0. But this function is only 0 at the origin. So the radius of convergence of the Taylor series is as bad as possible. It's just the point 0. This is why real analysis is much harder than complex analysis. So there's some stuff you need to do here, but the idea of the proof is we use this technique called differentiating identities to calculate the moments of our distribution. We happen to be in a nice situation where the moments uniquely determine the underlying distribution, and that's how we prove it's a Gaussian. So for the general case, what do we do? Well, in the Fibonacci case, here's a way of recasting what we've done, and it uses one of my favorite tricks. So let's let p and k as before be the number of integers that have exactly k summands, and my number lies between fn and fn plus 1. Well, I have to have fn over here. Turns out technically a little bit easier to look at how many lie between fn plus 1 and fn plus 2. So now I have to have fn plus 1, and then I have ft. What are the possibilities? If t equals n minus 1, well, the number of such numbers is just pn minus 1. If t equals n minus 2, it's p of n minus 2, so comma k. If it's n minus 3, p of n minus 3, comma k, and so on and so on and so on. So I have a recurrence relation. How many of you have seen recurrence relations with 2 indices? It is more than twice as much fun. Okay? So the question is, we know how to solve recurrence relations with 1 index. You all know the method of divine inspiration. Anybody divinely inspired right now? Anybody remember how to solve something like this? So we're going to play a trick, a very common game. I shifted to n plus 1. Well, let's look at what would happen if I looked at it at n. P, n, k, well, I just shift n by 1. Oh, look, it's a telescoping sum. So I can subtract, and I get a much simpler relation. I get Pn plus 1k plus 1 is Pn k plus 1 plus Pn minus 1k. And now that's a much simpler recurrence to investigate. It's now a fixed depth recurrence in the two indices. And there are games you can play. I'm happy to talk about them. The generating function is a little bit more involved. It's y over 1 minus y minus xy squared. You get your partial fractions. In greater generality, kn is the corresponding random variable associated with k. This is the case of the Fibonacci numbers, doing all the calculations. Here's the Fibonacci recurrence. The general recurrence relation is a lot more involved. Here's the Fibonacci generating function. The general case is a bit more involved. And again, absolutely amazing. This was all my student Yinghui Wang. She really persevered and was able to extract stuff from this. And so we then basically use differentiating identities as before. We use the method of moments, partial fraction expansions, and we prove everything exactly analogous to before. Okay, I'm not quite sure how long I was supposed to talk for. I figure, this is close enough to 7 o'clock. I don't want to go through the details of proving gaps in bulk. Everything is online, so if you're interested, I'm happy to stay here and chat, or just go online and take a look at the slides. The longest gap is a little bit more involved. I'm not going to go through the details of this. It took us 6 months to get the calculation right. We were off by a half. And so unfortunately, by being off by a half, we weren't sure which way we had to go, and it took a long time to track down the algebra error. This is why it's really good to do numerics whenever possible. Because the numerics were not matching our theoretical calculation, we knew we had a mistake somewhere. And the question was finding out where was that mistake. For those of you, how many of you have used Beamer to do a presentation? This is why you should use Darmstadt, because you can quickly click on different parts of the file. So just some references in future work. So some of my students this summer are going to look at generalizing this to other positive linear recurrence series. I want to try to look at removing the letter L and just look at positive recurrence series. What if I have something that's nonlinear? Do we have decompositions like this? The other thing is we can look at what we're calling F decompositions. So there are other ways to decompose numbers. And if people are interested, I'll talk a little bit more about some other ways to generalize this non-adjacency condition of the Fibonacci's. And it turns out there's other ways of looking at requirements. I really want to find a two-dimensional generalization of the Fibonacci non-adjacency, and I haven't quite done that yet. And then I will just end with a couple of links, and thank you for your attention.